Sir, shall we start? We'll start, I think. दासगुप्ता सर, shall we start, sir? आपका आवाज नहीं आ रहा सर.
You can start now.
Okay.
I'm ready. Whenever you are ready.
We are ready. We are ready, sir. We are ready because we don't
sure,
much
sure,
time, no? So we'll start. Nisha ma'am, please go ahead.
Thank you, sir. Good morning, everyone. So, for the two, will start introduce the sir. So, our today's speaker is the Dr. Sudev Dasgupta, sir. He is currently a professor and the head of the Electronics and Communication Engineering, Roorkee, India. He is the member of ITRI ETS, IST, and the associate member of Institute of Technology, Nanotechnology, UK. He has been a technical committee member, International Conference on Micro to Nano 2006. He's also been nominated as the in the USA awarded by Marcus 2006, 2007, and 2008. Has been acting as an expert member of the Global the Netherlands. He was awarded list of European Union in the year 2010 to work in the area of RDF at Polytechnic. He is recipient of prestigious IUSSF SSTF to work in the area of SRAM testing at the Madison, USA in the year 2000. With DAAD fellowship to work on the analog design using reconfigurable logic at TU Dresden, Germany in the year 2013. He has executed several sponsored research projects from MHRD and MICT Government of India. His current research interest logic for portable applications, low power application, substitution, radiation ICs, and development of 6T FinFET based RAD HARD design, effect on ICs, design and development of 6T FinFET and RAD and the HARD SRAM cell, novel semiconductor devices, FinFETs, PDSOI, FDSOI, nanoelectronics, semiconductor device modeling. So welcome, sir, for this session.
Thank you very much. Thank you.
Sir.
So shall I share?
Good morning.
Yeah, sir. Sir, you got us access.
Yes. So is this visible and I'm audible?
It's coming, sir. Yeah, it's visible.
Right. So let me start today's lecture. Shall I switch off my video or?
You can switch off, sir. No problem. If this full screen, full screen. Yeah, video you can, and this
Can you read?
yeah.
Just
So what happened, sir? Sir, you switch off video. Then bandwidth will be good. Video you can switch off. हाँ सर क्या हुआ? हेलो
हेलो हाँ सुनाई दे रहा है क्या? अच्छा एक मिनट रुको एक मिनट हाँ हेलो एम आई ऑडिबल? सुनाई दे रहा है क्या उसमें?
हाँ yes sir you are audible.
ठीक है okay sorry for the interruption. I will just stop my video and share my slides. There is some connectivity issue from my end, I suppose. So nonetheless, we'll start sharing the slides, and then. So thank you all for your invitation for presenting a topic in which I worked for quite a long time. So I thought of discussing with you a basic idea of low power design. So this meeting is about 1 hour, 15 minutes. And I will be presenting you the basics of low power design. And my name is S. Dasgupta, and this is my email ID. And this is the main building of our IIT Roorkee, which is about 150 years old approximately, a heritage building, which was built by British during the making of the Western Canal here in the western regions of Uttar Pradesh. So this is quite an old building. It's our main administrative block at IIT. With these few words, let me start with today's presentation, and let us see what we will be covering in this design technique tutorial sort of. So the introduction we will introduce, I will explain to you what power is all about. Since all of you are faculty members possibly, so I will go a bit fast in this case. And then we will use what are the various low power design techniques available with us, and then finally we will conclude the talk, right? So let me show you the motivation for such a talk. The motivation is something like this. If you look very carefully, then if you look here, then you see that only about 2% of the total volumes are basically of the processor. Whereas the revenue they earn for us is about 30%. Which means that volume to revenue ratio is very, very small, or maybe revenue to volume ratio is very, very large for microprocessors. Right? Whereas this is just the reverse for discrete devices. Discrete devices means if you use a bulk MOSFET, you take a bulk device, then its revenue to units volume ratio is very, very small. So therefore, most of the industry today, like all of big players of industry today, they are working on memory on the processor side in a detailed manner. They're working on the processor side in a detailed manner, and the reason being that the amount of amount of uh, amount of profitability is very high. Not only that, therefore, you require to work on optimizing the processor design. And one of the optimization principles is power. So how much power you are spending to do it. Now, as you are aware that that as you must be aware, what is the power? Let us look at the power trend with respect to year. When I say power, I mean to say the amount of power which the chip is dissipating over a period of time, right? That is defined as my power, right? And therefore, that is what the power is, which basically means that it is basically density or power per unit time. Right? So if you go ahead and then you will see it's basically a hot plate around 2000, and in 2005 it was basically almost like a nuclear reactor. And if you go further ahead, you will have a nozzle almost power density. And the reason being, you are actually following what is known as a Moore's law, right? Moore's law. Because there is a constant reduction in the volume and the length, and in any PET device, current is directly proportional to W by L. So if your length goes on decreasing, the current goes on increasing, and therefore ID square into R, right? That becomes large, and therefore the power dissipation goes on increasing. However, if this becomes so large, the power which you see, 1,000 watts per centimeter square, the silicon itself will start to show deterioration, and there will be a problem in the output trend of the deterioration. So that is the basic motivation for having low power design, especially for digital logic, right? So with this idea, let me show you how and this is, I think everybody knows that when input goes from high to low. So initially the input was low. So your PMOS, this is your pull-up network, right? This was on. This was initially on, right? And then when this is on, what is happening is the output goes to 1. That is what is happening. Output goes to 1. And the capacitor which you see here, this is the load capacitance, that gets fully charged from the VDD rail. So this is your VDD, and this is your fully charged CL. Right? And therefore, this is basically 1 to 0 transition. This is, so you're consuming power from VDD, right? So more larger, so higher or larger is the W band ratio of pull-up device, right? Pull-up device. More is the W band ratio. More will be the current, and therefore more will be the charging at CL, or faster will be the charging, and therefore low to high transition will be faster. Let's look at other. Therefore, energy consumption is directly proportional to the capacitor load. You're already aware that capacitor stores half C square and the total amount of energy stored in a capacitor, right? Where C is the capacitive load and V is the applied voltage on the VDD. So therefore, it's half C square. Now, therefore, the amount of energy stored therefore depends upon two factors: one on the capacitance and another on the voltage which you apply here on the VDD. So energy is proportional to the capacitive load. So one takeaway from all these discussions is that energy is directly proportional to the value of CL in a sense. Right? Now, this is, so you're consuming power from the VDD load, right? Now let's look at whether you're dissipating the power. Dissipating the power where? When this is on, right? When this is on, when this goes from 0 to 1. Then all this charge which was initially accumulated on the capacitor starts to discharge and go to the ground. And therefore the output goes from 1 to 0. And so that is what you get out of this principle of. So you're consuming, your power consuming cycle is when the input goes from 0 to 1, sorry, 1 to 0, and the power dissipating cycle is when the output goes from 1 to 0, right? And therefore, you will understand this basic point that the power therefore depends not only on the value of the CL, but it also depends upon the amount of VDD which you have chosen for the power to be there. Right? So that is what we have learned till now. Now let's come to an important point. So that's what I was trying to say, that the power consumption is only at 0 to 1 of the output. I think this is very, very clear to all of you, the audience. So let me explain to you. Let me explain to you about energy and instantaneous power. Right? And I'll explain to you what is the basic meaning of that, and we can then go into details of how can you reduce the power for for energy consumptions. Now, if you look very carefully, the idea here is that if you say, for example, you are going from a 1 to 0 transition. The 1 to 0 transition is which one? 1 to 0. So 1 to 0 primarily means where NMOS is initially on. Now I have got PMOS on, and therefore this switches on. And as a result, what will happen? As a result, there will be a charge being coming from VDD to CL. However, I did two things. Let us suppose this is inverter 1 and this is inverter 2. In inverter 1, my W by L ratio of pull up, this one W by L ratio, has got a larger W, right? Has got a larger W as compared to this one, which means that current flowing through PMOS for the inverter 1 will be larger as compared to current flowing through inverter number 2. Right? I think it's clear to all of you because your W by L is higher. And since current in a device is always proportional to the aspect ratio, therefore you will always get a current which is larger in dimensions. So since the current is larger and you need to fill up the same amount of capacitance, right? This is capacitance is same. Obviously, you can think that this will be filling up faster as compared to this. And therefore, you see the rise is very, very fast in inverter 1 as compared to inverter 2. So what I'm showing is TD1 is basically the delay because of inverter 1. So this is 50% delay between input transition and output transition. And that will be relatively small for case of 1. Whereas for case 2, if you look carefully, is quite interesting. Case 2, your delay is much larger. And this is true also, and this is true also because since you're so at the cost of power, your delay has actually increased in the second case. Since your lower transistor inverter 2 has got a smaller W, therefore current is smaller, therefore ID square into R is small, and therefore the power is small. But the cost you pay for it is a higher delay. So power and delay, they never go hand in hand. This is the first takeaway slide in a VLSI design, any design principle, especially in digital design, that power, if power goes on increasing, right? If power goes on increasing, that generally is offset by a reduction in the delay, right? And vice versa. So if the power goes down, your delay will also go up, and you will have a slower system to work with. So generally, therefore, low power design is associated with slower speed on chip speed. So that's what I was trying to say. That the first, the same, so same energy is same. Why energy is same? Because you're just doing half CV square, right? You're doing this half CV square. The half CV square is same because I'm not changing the capacitance or I'm changing the VDD. Therefore, the energy is same. However, my inverter is faster as compared to inverter. Right? So therefore, let me show you the matrix which I wanted to show you. So if you plot power versus time, if you plot power versus time here, right, the first approach that will be able to have a larger power, right? But the time will be reduced drastically. So the delay was reduced drastically. Whereas in the second case, the power is small, but the time is large, so delay is large. But the area under the curve, which is this one, is the energy, is exactly the same for both the cases. So what we have learned, therefore, is the energy is area under the curve. Therefore. So that is it. So I can have a high power for a larger duration, high power for a smaller duration of time, or a low power for a larger duration. And therefore, we generally refer energy to be equals to therefore power into delay. That is the first equation which most of the digital designers take care of while designing any digital logic. So power into delay, where power is the power dissipated, it is a capital D is a delay, which is available. Now, what are the various matrices? What are the problem areas? So, how much energy you are dissipating? How much energy you are dissipating is determines the battery life of your system. You will see that many of the mobile phones which you are using nowadays, they claim that the battery life is very large. And how does it work on that? Because we will see that in most of the mobile phones today, which uses 4G mobile systems, the most two important power hungry elements of a mobile phone are your screen, which means your LCD or LED screens, which you see here, touch screen especially nowadays, which is very power hungry. And the second thing is the transceiver, which tries to communicate with the tower, right? The mobile tower, BTS base station. Now, so if you want to conserve power or you have to extend your battery life, the two ways of doing it is that let us operate in those areas where. So if you will automatically see that if your network is very strong near wherever you're staying, your battery life is relatively extended, right? Second thing is this is known as uh, uh, extrinsic parameters for the battery life. So what are the extrinsic parameters? Extrinsic parameters are your base station, right? Base station, and then your extrinsic parameters are also your power supply. What are intrinsic parameters? Intrinsic parameters for any mobile phones are two things. One is your processor speed, right, and application. What does that mean? So if you're doing a very high-ended video application, you will be using large amount of energy, and your battery life will go down. Similarly, if you're using a Snapdragon Qualcomm processor, it will consume slightly more power as compared to say ARM processor, right? At the cost of a higher speed and better functionality. Right? So these things do matter, right? And they set the power limit. What I'm talking here is at transistor level, how can I reduce the power? The second aspect which you should be aware of is what is known as a peak power. What is the meaning of peak power? Peak power primarily means that power which is not always available to you, but it might show a very heavy peak at certain specific periods of time. So this is basically at T tending to 0, right? So this is T tending to 0, sort of a power peaking at a particular point. For example, you have an IO buffer, right? You have IO buffer, you have a chip, and then you have got IO pads here, and so you see that suppose this IO pad is a data-centric IO pad, and this is clock. This one is clock, let us suppose. You will see that the clock will always have a larger peak power as compared to the IO block with data. Because clock has got an activity factor of 1, which means that always the clock is rising or falling. And as a result, you will always have this change in the power dissipation. So this power also defines your noise margin. I suppose all of you are aware of noise margin and reliability. What is reliability? Reliability basically means that if you are operating the device under stressed conditions, which means high VDD or very high electric fields, then how much lifetime of the device is. Right? So we have learned these two things effectively here. Two more important metrics for power before we move forward, we need to know is what is known as a power delay product. So this PDP is what is known as a power delay product, where P is the power and TP is the delay, and it is referred to as, and its units are basically joules, right? And this another is energy delay product, so that's PDP into TP. right? So you see, EDP has got a higher weight of TP, whereas PDP has got almost a linear weight. So PDP, if you look very carefully, PDP is directly proportional to TP, right? Whereas in the second case, PDP is directly proportional to TP square. It's square term which is coming into picture in the first case, right? So these are the quality criteria. So whenever you're told to design a digital processor or any processor, you will be given these two parameters. For example, energy delay product is, I'll give you an example. Let us suppose you want to do an operation of, let us say, 4-bit addition you want to do. So there are 4 bits, and so there's a 1011, let us suppose, and I'm adding with 1100, let us suppose, right? And I want to find out the energy. So the way of doing it is that you just carry this operation, 4-bit operation, right? And then you say the amount of, so, and you find out, let us suppose your energy is something, some say X. And then you divide that by the number of bits which you have used, and that is 4. So the number of energy per unit bit is X by 4, right? So this happens to be one of the major criteria when you are designing a processor. And you will see here that the delay has got a relatively much higher weight as compared to in EDP as compared to PDP. So many people go for PDP when you are looking into power, and many people go to EDP when they are going for energy delay product, right? Now, as you can see here, this statement that right, two independent designs, can have the same PDP, even if the TP is 1 year. So if your delay is 1 year, your power dissipation will be very, very low. And therefore, you can do a job in, say, theoretically in 1 year, one job, and you can do in 1 second also one job. Right? So in the second case, you will automatically have a much larger power dissipated as compared to the first case. Okay? So where does the power go? And I suppose so most of you are teachers here, and you must be knowing all these things. I can go a bit fast. So there are 3 powers which are already known to us. One is known as a dynamic power dissipation. Another is known as the short circuit power dissipation. Another is known as the ES power dissipation. So there are 3 power dissipations generally which is available, right? So let us first concentrate on the dynamic power dissipation. We already learned this fact that you are charging and discharging it, and dynamic power dissipation is given by the formula which you see here. I'll go on explaining each one individually, and then we can carry forward. Maybe I just okay. Now you see here, as I discussed, so CL into VDD squared is the power, right? CL into VDD squared is the dynamic power which you see. Why are you multiplying that with P0 to 1? P0 to 1 is the probability for the output to switch from 0 to 1. Because that is the only time when the capacitor is actually getting charged from within. So P1 to 0 is the only time when it is dissipating power. When it is consuming power is when the output is going from 0 to 1. And therefore you multiply that with the probability that the output is going from 0 to 1. Now, why do you multiply with F? F is the frequency of the system. What is this frequency? This frequency is very simple. This frequency is that, therefore, if there are n number of clock cycles, and if your probability is 0.5, then n by 2 times you will have 0 to 1 transitions available, right? You got the point? So if there are, let us suppose, n clock cycles. N clock cycles means n times 0 to 1. So it's 2n times. So if there are n clock cycles, you will have 0 to 1, 1 to 0, 0 to 1, 1 to 0 transitions taking place. So for every 0 to 1 transition, if I assume that your PMOS is getting on and your CL is getting charged, therefore for every n by 2 cycle, right, you will have this power being consumed. And that's the reason I write down that P is the probability that the output goes from 0 to 1 multiplied by frequency. Where frequency is the frequency of the operation. We replace this P0 to 1 into F by what is known as alpha. into F, right? Alpha is basically defined as the activity factor. This is also referred to activity, or some books or some papers write down this as activity factor, right? Activity factor. Now, what is activity factor? I will explain to you there. So you see, the effective frequency is actually less as compared to the clock frequency, and it depends upon the activity factor, which means that not every, so for a transistor, for an inverter, I can agree, but for some complex logic, uh, uh, 0 to 1 transitions will not uh, result in an output of power consuming circuit. So therefore, what we found out was that the output power is a function of switching activity. This is very important. That your output power is a function of switching activity. Therefore, data dependency is there, which means that how does your any gate, right? What type of input are you giving, and what is the level of transition of an input happens to be very important. I will give an example here. Let me help you out. So, for example, if it is a NAND gate, that is 0, right? And then 0, 1, 1, and then it is 0, 1. So there are two input. It's a two-input NAND gate, and then 0, 0 will give you output will be 1, right? And then 0, 1 output will be 1. And this will be 1, and this will be 0. So you see, if the output goes from 1 to 1, or this one to this one, or even this one to this one, right? This one to this one. It is not consuming any power from in the output side. It can only consume power when it goes from this to this, right? This to this, or even this to this, right? Or even 0 to 1. So you see, 0 to 1 transitions are not always possible. So therefore, if you look at the state FSM, then these FSMs or these state changes from state number 4 to 3 to 2 to 1 are only power consuming cycle. Any other are non-power consuming cycle. And therefore, the type of data which is inserted into a system will determine the dynamic power consumption. Let's look at the short circuit power consumption. What is short circuit? Does it mean is that in the input side, when the input goes from low to high, right? Input goes from low to high. Then, if you remember that when the input was low, PMOS was on, and when the input was high, NMOS was on, right? Now, somewhere in the middle, therefore, logically speaking, there will be some amount of voltages for which this both PMOS will be on and your NMOS will be also on, right? As a result, what will happen is there will be a short circuit path between VDD and ground, right? So there will be a very heavy current flowing from VDD to, right? And that small period of current is given at for a small time TSC. TSC is a short period of time, because of which there's a direct.
It is not changing.
Direct. Hello.
I think PPT is not changing, sir.
Oh, it is not changing.
No, sir.
Oh,
And it
what is the?
also is not showing. It is only on dynamic power dissipation, sir.
Okay.
No, sir, it is changing, madam. I can see it is changing.
Okay,
So
so
it is
from my
slight.
side it is not changing. So I thought I will check my network.
Anybody else participant? Can you unmute and see the slide? Should be short circuit power consumption.
It is changing, sir.
Yes, sir. It is changing. It is changing.
It is changing, sir. Okay. Yeah.
Okay. Thank you. Right. So I hope it is changing. So there's a direct path between VDD. There's a direct path between VDD and ground, and because of this, there's a short circuit current. Right? And but the problem of this is short circuit current is it will happen. It will happen twice. Why twice? Because when the input goes from high to low, and when the input goes from low to high, in both the cases, you will have short circuit current. So it's basically twice. So you will have a short circuit current like this spiking here, right? And you will have a spiking here. You can have two spikes available here. And if you look, therefore, it is the probability of 0 to 1 transition and the probability of 1 to 0 transitions. Why they are added up? Because they are totally two independent operations. And therefore, simple addition will help you and you don't have to multiply as you did in the first case. So the probabilities are added here in the second case, whereas probabilities are multiplied in the first case, where you multiply the activity factor. The third consumption is leakage power. Leakage power is, again, there are two types of leakage power. One is the subthreshold leakage, another is the gate oxide leakage. Let me explain to you gate oxide leakage first. And the gate oxide leakage is that because the silicon dioxide is getting very, very thin and you have a large voltage on the gate side, you can have a direct tunneling between the oxide layer through the metal layer onto the drain side and the source side, because of which you will have a large gate oxide leakage. Right? What is subthreshold leakage? When the gate is operating less than threshold voltage of the device, you will have subthreshold current flowing through the circuitry, which will be relatively high in the case when your VDS is relatively larger, and therefore the subthreshold leakage will be there. As I can see, therefore, what I simply do is I add these two currents, I subthreshold plus I gate, and then multiply with VDD. Once I multiply with VDD, I get the total leakage power. So what is the final equation of power in a CMOS? It is given as alpha times F times CLVD square, where alpha is the activity factor. I do VDD into I peak into P021 plus P120, which is short circuit power, and we come to the final, which is the leakage power. Right? And the short circuit power and leakage power. But the current problem is that your dynamic power is decreasing, and short circuit power is also decreasing, but your leakage power is increasing day by day, and that's the problem area currently, as far as designers are facing. Right? Then let me explain to you what is activity factor. Well, that's very simple and straightforward. I can explain to you by a diagram, and we will understand. So let us suppose I have a clock, and this clock goes from 0 to 1, and there are 4 clock cycles available with me, right? There are 4 clock cycles, and these 4 clock cycles are given as this, right? So there are 4 cycles. Sorry. So let me do another clock cycle here. And let me do another clock cycle here. So there are 4 clock cycles. I apply these 4 clock cycles to any particular gate. And let us suppose I see only one in the output of that gate, 1 0 to 1 transition. There's only 1 0 to 1 transition. Then we define activity factor as 1 divided by 4. That is equal to 0.25. So the maximum activity factor which you can have is how much? Is 1. Why 1? If you have a clock, and if every time for rising into the clock you get something like this, then it is defined as alpha is equal to 1. Right? So which means that if the number, so you divide the number of transitions in the output to that of number of transitions in the input, and that is what is defined as the activity factor. So generally, if the signal is a clock, activity factor is always equals to 1. Signal switches only once per cycle, then it will be 1 by 2, right? Because a cycle has 2 clocks, 1 by 2, right? Typically, in all static design, alpha is of the order of, generally of the order of 0.1, typically, for any, and more complicated the gate is, lower its value of alpha, right? So the cost of area, your power slightly goes down, and your performance also goes down. So that is how we define activity factor. Now, static power I discussed with you because, see, so in a CMOS logic, if you remember, in a pseudo NMOS logic, if I use a ratioed logic, like for example, a pseudo NMOS logic, then I will, there is some problem with my pen here, but anyway, so what I do is a PMOS, I generally ground it, right? I ground it here, and then I apply a potential here and go. So this is known as a pseudo NMOS logic, also known as ratioed logic. There will be this will be normally on device, and therefore there will be a fight between the pull-up device and the pull-down device. There will be a relative fight between the two, and as a result, you will consume a larger static power in case. Hello. Hello.
Yes, we are hearing you, sir.
Okay, so can I carry on?
Yes,
Yes,
sir,
sir,
please
clearly.
continue.
Okay, thank you. So there will be a relative fight between the pull-up device here and the pull-down device here, which is basically an NMOS. So there will be heavy leakage current, which is basically a threshold leakage current. Not only that, your threshold voltage also changes because of a substrate bias. This is VSB. Because of substrate bias, if the threshold voltage changes, you actually draw larger power, right? Let us say the threshold voltage goes down, right? Because there's a negative sign here with sigma. This is Dibble effect, and therefore with larger value of VDS, the threshold voltage goes down, which means that you are actually operating with threshold voltage of 0.5, and you reduce your threshold voltage and you reduce the gate voltage to 0.4. But then because of Dibble or because of other effect, your threshold voltage has gone down. You are forced to go into subthreshold region because of which the static power actually becomes higher in case of ratio. So let me give a brief example of a ratio example. Let us have a pseudo NMOS decoder, and there are 24 bit lines, and so let us suppose I have a chip with 32 words and 48 bit lines, and let me find out the static power consumed by ROM. You will see that if I use pull-up devices, which are basically CMOSs, then and assuming all of them are in ratioed logic, then the sigma I the pull-up current is 24 microampere, and therefore power is equals to VDD into I pull-up, and therefore that is 29 microamp, right? Because typically we use a 1.1 volt supply, and therefore static power happens to be equals to 24 microamp plus 31, because 31 is approximately the VDD. Sorry, I've not used the whole. I've not shown you the whole example, but what I can simply say is that power for one device, right? Pull-up device is 29 microwatt, right? And since there are 24 bit lines, so 24 bit lines we are adding here, 24 plus 31, because they have 32 word. So there will be 0 to 31 will be the word line. So for every word line there will be one pull-up, and for every one bit line there will be one pull-up. So I add these two together, I get 1.6 milliwatt. So you see, simply a 32 word into 48 bit ROM, which is the cache ROM in your laptops, in your memory, while starting, it consumes 1.6 milliwatt of power just because of the static power of the ROM, right? So what are the ways of reducing leakage power, right? So the one way is let us take two types of flavors. That one is having a leakage of 20 nanoampere per micrometer for low VT. Another is having 0.02 nanoampere per micrometer for high VT. So you see, a low VT has generally a higher subthreshold leakage as compared to a high VT, right? Similarly, if you have a thin oxide, you have a higher leakage, which is 3 nanoampere per micrometer, as compared to thick oxide, which is 0.002. Right? You pay some cost for high VT and thick oxide, but then your leakage currents are drastically reduced. So typically, when in a ROM type environment where you will be accessing the ROM maybe once and then it will be switched off, or maybe working in subthreshold logic, it is always advisable to use low leakage transistors with high oxide thicknesses, so that and high threshold voltages, so that you don't worry. So see, so the generic idea is, whenever you're using a low switching activity design, try to use a high VT and low leakage or a thick oxide design into consideration. That will make your life easier. So memories, for example, typical, not SRAMs, but memories like ROM, you generally use low leakage transistors everywhere, right? And gates use low leakage transistors for 80% of the logic. Now, if I use this low leakage variant, and I will not be able to explain the whole diagram. It's very simple. Otherwise, you see, you are just consuming 38 milliwatts of power, right? Your static powers are 38 milliwatt, right? Whereas if you use a low, so if you use the high leakage device, right, and if you calculate the power, it is 0.749 watt. So you see 0.749 watt, which is relatively a very high power which you see, right? So the first thing which we learn out of the low power design is whenever you're using an arrayed architecture, a ROM, and you're using a relatively large ROM, it is always advisable to keep it to be high TOX and high VT devices in order to reduce your subthreshold leakage. So let us see what are the low power design techniques now. So we have understood by till now, which is about half an hour of our talk, we have understood 2 or 3 important points, and those 2 or 3 important points are what is power, what are the various parameters of power, and what are the origin of power, and why we are motivated to have such a talk in terms of low power design. So I suppose all of you are aware of these basic fundamental principles. Now we enter into the second part of the talk, wherein we try to give you an idea about various techniques, both at device level and at architectural level, how to reduce the power. The first, we will be looking into dynamic power, right? So there are 3 components. I will look into dynamic power. In the dynamic power, as you are aware, so first thing is try to reduce your alpha. Right? Try to reduce your alpha. When you reduce your alpha, just a minute. Huh? Because sorry. So one way of reducing dynamic power is to reduce alpha, right? Is to reduce alpha. Reduce alpha basically means reduce the activity factor. How to reduce the activity factor? We will see later on how to do it. But typically, if you convert from NAND to logic to a NOR to logic, because so NOR to logic, then we will show later on. Maybe we can time permits alpha will reduce. Confidence to me because start of the meeting. So right. So this is what you get. So this is one thing. So the second thing is that you apply a sleep mode. Sleep mode is very simple and straightforward. See, the problem with this, with the design which I told to you was that let us suppose it's very simple. It's almost like human being. So if you're not working, right, then it's better you go to sleep and conserve your energy. Exactly same thing happens in digital logic. So let us suppose a part of the circuit is not working for a period of time. You very well know that. Say, for example, you are processing video. Then you will be using a huge amount of DSP architecture for doing signal processing, right? But then you very well know that your other logical blocks, right, will not be utilized too often. So you apply a gate there and keep the gate off, and therefore you can just deactivate that module from the rest of the chip, and therefore all the power in that chip will be going to 0, and you will be able to reduce your dynamic. The second aspect is use small transistors. And this is quite interesting. See, currently, if you know if you're aware of the architecture, which is von Neumann architecture, which people follow in digital logic design, you have let us suppose an amplifier or a structure, and then you have interconnects, right? And then another structure is there, and so on and so forth. That is generally what you do. So sorry, this is not von Neumann, but this is an architecture which I am trying to say, right? कुछ प्रेजेंट है आनंद से बैठो कुछ बोल रहे हो नहीं वो स्टार्ट हो गया बातचीत चल रही है वहां पे शिव को जरा बुला के लाना शिव कोई बैठा हो शिव sorry I'm extremely sorry I have another meeting going on in parallel so I need to coordinate that as well I'm sorry so you see therefore if the intrinsic delay of this block if the delay of this block is much larger as compared to the delay of the interconnect, right? If this delay is larger than the interconnect, then it makes sense to make it lower delay. Whereas if the reverse is true, then any change at this stage makes no sense, right? So you should be aware of whether your digital design in a block cells gives you a larger delay as compared. So if your interconnect lengths are very, very long, then are you spending more power and higher delay in just transmitting one bit of information from point A to point B? So therefore, typically use short wire so that you are reducing your interconnect delay, and also use small transistors. Then the area of the transistors are lowered, and therefore the capacitance is lowered, and therefore your dynamic power is. The third aspect is that please use lowest suitable VDD. Right? So typically the rule of thumb is that if you're using, for example, a 180 nanometer technology, then it is 1.8 volts we generally use. So into 10 is what the typical flavor is. So if you're using a 65 nanometer, then please use 0.65 volts as the VDD. मीटिंग स्टार्ट हो गया मीटिंग स्टार्ट इंडिविजुअल मतलब उन लोग गोवा ये पटना वाला स्टार्ट कर दिया कौन कर रहा अभी तो जस्ट स्टार्ट किया है जस्ट अभी 5 रेडी नहीं है तो कोई ज्वाइन किया वहां पर है मतलब सब नहीं कर रहा अच्छा तो जस्ट वो आनंद ने बोल दिया कि पहले इंडिविजुअल स्टार्ट करो हाँ तो वो स्टार्ट हो गया मतलब कौन गोवा पढ़ रही है नहीं अभी तो जस्ट पहली बात कर अच्छा ठीक है तो उसके बाद हम लोग को फाइनली आएगा लास्ट में तो मैं फिर यहाँ पर ना मैं आऊँगा so that's the rule of thumb sort of people are following, and it will be into 10 which people follow, and therefore you will have 1.8 volt, 0.65, and so on and so forth. So generally use the lowest suitable voltage which is available with you, and also use the lowest possible frequency, right? So this is what people do. There is another technique which people follow, and that is, I hope you have heard it, is what is known as GALS, right? GALS basically means globally asynchronous, locally synchronous. See, the idea is that if you have a synchronous design, right, then if you have a synchronous design, the problem is that with synchronous design, the problem is that since you will be using the clock, you will be spending large amount of power in just synchronizing the whole circuitry. So what people do is, rather than having a global clock for the whole chip, let's have the global part asynchronous, and only in those areas where you require synchronicity in terms of data transfer, for example, a flip-flop or so, make that one locally synchronous, right? That way also you can reduce your dynamic power. How can you reduce the static power? So the way you can reduce is use ratioed circuit, but selectively use ratioed circuit. Now, static power reduction, how can you reduce selectively is that those domain where your noise margins, so generally don't use ratioed circuit in memory because noise margin gets compromised. You can use ratioed logic, not even in computation as such. You can use it where you just simply have to go ahead and do, say, for example, in inverter. There you can use a ratioed logic. Second thing is selectively use low VT devices, right? Selectively use low VT devices, which means that if your threshold voltages are low, just use those devices at critical paths and not in all the paths, right? And how can you reduce reduction? I will just explain to you. Stack devices and body bias and low temperature are the various methods by which you can reduce the leakage. As I discussed with you, therefore, reducing VDD has a quadratic effect, right? Why? Because it is, remember, power is dynamic power is directly proportional to VDD square. And what is happening currently is that you are reducing VDD, right? Actually, they are saying you will start with the. So आनंद सर बोलेंगे तो मेरा तो I'll take 15 more minutes. Just wait for 10 minutes. Sir is coming. 10 minutes. Sorry. So we will so we will have VDD reduction. So we will have a VDD reduction, right? And the problem is with VDD reduction is that VDD approaches 2 VT approximately. 2 VT approximately. Then that is the minimum value of VDD which people follow, right? That's the minimum value of VDD which people follow. The second is lowering CA. Lowering CA will obviously improve the performance and keeping the transistor size minimum, and also reduce the switching activity. Switching activity basically means that because it is impacted by logic as well as architecture, right? And that will reduce the switching activity to a larger extent. So transistor sizing, if you look very carefully here, what I do is if I want to go for a large, so if I have a small W and I go to large W, right? Then what I will do is if I have a small W, my capacitance will be lower. If I go to large W, capacitance will be higher. But if I go for large W, I can actually get the same current for a lower, because my Ws are larger and therefore I can get the same current at a lower voltage. And therefore, if I want to have a smaller W and I want to the same current, it is advisable that you make a higher voltage, which means that to keep the performance the same level, in fact, when I say performance, I specifically mean delay, then I will just use a smaller W, right? I will use a smaller W. But a smaller W will mean that I have to use a higher voltage in a sense. So I have a larger size devices, and therefore, when you use a larger size device, then you can specifically work with lower voltages. And when you use a minimum size device of smaller Ws, generally it is used for the same amount of delay, higher voltage is required, and therefore use more power for a lower voltage. One thing which I just therefore will go a bit fast in this case and explain to you what is important. Let us suppose I want to use this logic, right? I want to design this logic. Y equals to A plus B dot B, nor of that. So I'm landing it. So what the idea here is that that it is always advisable to keep the highest activity factor data closest to the output, right? It is always advisable to keep the highest activity factor data closest to the output, which is which output? The Y output here, right? It is always advisable to keep it at the Y output here. Which one? The highest activity factor activity factor. Now, if you see here, the most highest activity factor device, if you see, is basically a B, right? Input B is the highest activity factor, and it's max. So you see, if you keep it very close to the output, you save 19% of the power. Whereas if you keep A1, which is next one, then you're saving just 10% of the power. So therefore, for given logic function and activity, please keep the signal with the highest activity closest to the output. That is one thing which we learned, so that you can reduce the charging and discharging of internal loads, right? One thing just I wanted to come to you is Dr. Rathod.
Sir.
Can I do one thing? Can I do one thing, because I'm there's another meeting which requires my intervention. So can I close here, and then rest of the topic I can take at 3:30 when I will be starting my next session. I can extend that session by half an hour.
Yeah, no problem. You want to take in the afternoon slot?
I can take in the afternoon slot from 3:30 to 5:30.
3:30 to 5. Okay, no problem.
So what I will do, the first half an hour, I will just start with this low power design.
Okay.
And then next challenges in researches areas of VLSI. What are the various challenging techniques or research techniques in VLSI design?
Okay, sir. Okay. So you want to stop now and come back at 3:30?
Yes, yes. At 3:30 and explain, and then take about half an hour of this one and then next one.
Okay. No problem, sir. I'll continue with.
I'm extremely sorry to all the audience. I was supposed to stay here at 11:15, but actually the other meeting which is there with the ministry for my project, that has already started. So I need to go there also. So I'm extremely sorry. I will join you at 3:30 then.
Okay, no problem, sir.
Okay, thank you very much.
Okay, sir. Okay, sir.
Okay.
So participants,
I will answer the questions also at that point of time. In the meantime, if you have any questions, you can. In the meantime, if they have any question, they can write to you, And those questions
Okay.
can be asked during the this thing.
Okay, sir. Okay, no problem, no problem.
Okay, thank you very much. Thanks, sir.
Okay, sir. Okay, okay. So, participants, what we will do is, it's already an 5, so we will have a 5 to 10 minutes break. I will give you, and then I will take a session now. I will engage you up to, let us say, 1.5 hour, up to 12:45 or 1, and we will talk about the system verilog. So verification and system verilog concepts, which probably yesterday there was a gap, like he was trying to explain what are assertions, something like that. So we will have a basic introductory section about verification and system verilog. So I'm giving you 10 minutes break. In meantime, I will also prepare, I will search the material and I'll keep it ready. Only 10 minutes, okay? So thank you very much. Join by 11:15 to 11:20. We will have a session, huh? Sneha madam, are you there? Madam, आपने सुना है present?
हाँ सर।
वीडियो
हाँ
दिखाता हूँ,
सर।
आपको आवाज आता है कि मुझे नहीं पता। हाँ
हाँ,
ठीक है, मैं वीडियो दिखाता हूँ, जस्ट आपको आवाज आता है कैसे बोलना, ठीक है?
ओके सर।
आ रहा है।
देखा।
आ रहा है
आ रहा
सर।
है?
आ रहा
आ
है
रहा
आ
है
रहा है।
ना?
हाँ।
बस that's it. Okay. And switches this. Okay. Shall we start?
This call पर
Pam madam? Oh, Shaila
sir,
madam?
there used to be some problem. I was not. Hello.
Audible,
Hello.
audio problem. हाँ मॅडम ऑडिओ प्रॉब्लेम. तुमचा आवाज येतोय.
Yeah, audio.
We are able to hear you मॅडम. मॅडम आता कटला आवाज, आता नाही आला व्यवस्थित. आता नाही आला मॅडम. नाही मॅडम. नाही येत आहे. नाही. No, no, no. I am not able to hear you clearly.
बघा माझा.
नाही मॅडम नाही. मॅडम चॅट बॉक्स बघा, मी लिहितो वाटल्यास.
तुम्हाला प्रॉब्लेम आहे का?
मी अरे तुमचं नाव मी मॅडम मी तिथे लिहिलंय शैला मॅडम युअर व्हॉइस इज ब्रेकिंग. हा येस.
सर.
ओके. हा मॅडम.
आय एम एबल टू हा मी तुम्हाला इव्हन चॅट बॉक्स मधून करस्पॉन्ड करतो म्हणून व्हॉट्सअपवर मेसेज दिलाय.
ओ
सर माझा मेसेज पण चॅट बॉक्स.
मॅडम तुमचं या प्रॉब्लेम नाउ व्हाट डू वी डू. बाकी पार्टिसिपेंट को सबको क्लियरली आ रहा है ना आवाज सब कुछ. मैडम इंटरनेट प्रॉब्लम. यस.
Yes, sir. Voice is clear, sir.
इंटरनेट बट कल मैडम का सेशन है. ओके मॅडम, जर तुम्ही बघत असाल तर बघा कसं मॅनेज करता. ओके shall we start? Yes, we already. So I'm launching a one poll question, and just see that poll box, chat box. Yes, madam. Hope it does not arise tomorrow. Correct. I'm opening a poll, so just to know. Okay. What is this? Okay. So I can see that many of you have written either not started, I know, but have not worked, or no, it's a very little idea. Okay, I'll close the poll. I can share the poll with you. You can see. Okay, that means I'll have to take you through this, what is verification. So let us have discussion about verification. So first, you give a video, one or two videos, one by one, and they are very few seconds. So I would like to know your comment in the chat box about that particular video. Okay, let us go for first.
हैंडबैग का पिक्चर देखा? अच्छा है ना? रेड है। कैसा रेड?
चेरी रेड, ब्रिक रेड, एप्पल रेड, ब्लड रेड।
अरे पिक्चर में देख लो। क्या? ऑरेंज दिख रहा है? हाँ। अपने फोन से खींच के भेज दे।
सर, इसीलिए तो हर लावा फोन पे हम हजारों टेस्ट करते हैं, so that it never lets you down.
Never lets you down.
So I want you to write if audio, video, everything was visible, your interpretation as an engineer of this video. Fast, quick. One word, one line is more than no paragraph, please. Was it visible, audible, audio, video? पायल मैडम, ऑडियो वीडियो था, क्लियर था?
हाँ सर।
Okay, okay. I want one word fast. Okay, if you are not able to get from that video, I'll go to next one. I'll go to next one. Okay.
हैंग हो गया। धीरे से स्वाइप करके देखिए।
कॉल आ जाएगा।
आ गया। टीम मैनेजर, हेलो सर, हाउ आर यू? हाँ, मैसेज ले सकता हूँ। अच्छा अच्छा अच्छा, कॉन्फिडेंशियल। क्या बात है? मदर प्रॉमिस।
मैसेज बताएगा?
सर, हर लावा फोन पे हम हजारों टेस्ट करते हैं, so that it never lets you down.
मैसेज बताएगा?
सर, माँ की कसम खाइए।
Never lets you down.
Any keywords? Anything? Okay. Testing. हजारों टेस्ट. Testing. Lots of test to verify. चलो, और एक बताता हूँ. दो बताने का है मुझे, और एक at least let us go for one. Short videos. Try to differentiate between videos also. Video to video differentiation.
तो आप चाहते हैं मैं लोगों को बोलूं कि आपका फोन बहुत रिलायबल है।
सर, लावा का हर फोन हजारों टेस्ट से होकर गुजरता है।
मैं कैसे मानूं?
सर, आप खुद एक्सपीरियंस करके देख लीजिए।
ओहो, गलती से गिर गया। टूटा तो नहीं?
नो सर, हमने इसके लिए भी टेस्ट किया है।
Just one of the 1,000 tests that make lava phones so reliable.
ऐसा कोई टेस्ट जो आपने नहीं किया हो?
सर, वो आपकी
Never lets you down.
So some difference between three. First, second, third. Try to recollect what I had shown. Complete with the last one, and then you can write.
लोगों को ये बोलने से पहले कि आपके फोन्स रिलायबल हैं, I have to be sure.
वैसे लावा का हर फोन हजारों टेस्ट से गुजरता है।
एक्स्ट्रा टॉवेल लाना चाहिए था। मंगवा लेंगे। ओह नो, फोन अंदर ले आया, खराब हो जाएगा।
नो सर, इसके लिए भी टेस्ट किया सर।
Just one of the 1,000 tests that make lava phones so reliable.
कोई तो प्रॉब्लम होगी।
एक प्रॉब्लम है सर।
क्या?
टॉवल।
Now I want the differentiation between four. What lava? Obviously, we are not promoting lava. It is just for our understanding purpose. But what was the difference between those and why it was so important that a company like Lava is promoting it in a different manner? Quality, verification, testing, durability. Any difference between the four as far as tests are concerned? Can you write a comment? Okay. Any other comment? What was the verification carried out in the first video? If you remember, in first video, it was about the backer of the bag. So what they are trying to claim? Good in that. Yes, camera, correct. Camera processing unit. It's very good. That means, and people do like it because now there is a word of selfies. People like it. Yes, in terms of engineering terms, it's an image processing, very powerful image processing. You can say. Okay. In second video, what was the problem? They were playing the game. Suddenly, a phone call comes, and then Dhoni was not able to pick up the call. The another person picks the call, and that's what happens. So, what is the message in the second video? Okay, CPU speed. Okay, multitasking. Yes. So that means your phone is capable of handling multiple tasks, many tasks parallelly. It doesn't get hanged. Correct. It doesn't give any issue. Multitasking. Yes. What was the third? The drop test. It picks and the drops mobile phone. So that is, you can say, the mechanical rigidity. Okay, drop test. It is a kind of a mechanical rigidity. And what was the last test? Last video. About the humidity. Environment was humid, and still that phone was taken inside. Correct. So different start many tests, हजारों टेस्ट से गुजरता है. But have you noticed one very important statement of Dhoni, particularly last two videos? ये बोलने से पहले आपका फोन रिलायबल है, you have to be sure. Am I right? कस्टमर ये बोलने से पहले आपका फोन, you have to be sure. Correct. So this is the starting of this particular concept, or you can say course, that is a verification. So I will share my screen now with the PPT. So now PPT visible? One, Pal madam? Okay. We'll go ahead with this. So what I'll try to do is, I'll try to explain the little basics of the verification and the system Verilog together. Correct? So yesterday's session, the morning session or in the afternoon session, he has used many words which probably I could interpret that audience was not aware of, and therefore I'm talking about this. This I have taken right now this particular topic rather than digital VLSI or analog VLSI or mixed signal VLSI. So I thought that let us give a brief about the keywords that are used in verification, and that's why. So you can see that these are the keywords which are used very popularly in the verification nowadays, verification environment. And those keywords are, first of all, a system Verilog. So we need to talk about what exactly the system Verilog in brief, let us say. Nowadays, yesterday also we have used sometimes randomization, right? Randomization and IPC. IPC is called as inter-process communication. And next is a coverage. In the afternoon session, he was talking about the coverage, but I could see from the chat box that people were not aware of the coverage. And then the assertions. This is another buzzword and very popular word nowadays, assertions. And we have object-oriented programming methodology-based verification, right? So this entire verification cycle, system design FPGA based system design is around this particular thing: system Verilog, randomization, communication, coverages, assertions, and OOP based methodology, right? So this 1 hour, let us say 1 hour or 1 hour 15 minutes, I will try to explain you these keywords. We will not go into the syntax of the language, but we will also open some software or some other you can say tool set through which I can demonstrate at least few examples, right, to you. So this is what you have seen in the video, a kind of a product. There are many electronic products, and when any company sells such kind of products, there is an integrated circuit inside this, and that circuit might be a kind of a system on chip nowadays. Mostly it is a system on chip, right? So when you talk about system on chip, there are so many complexities involved in case of system on chip. So there are two aspects to any system on chip. One would be you can say verification. Another would be a testing. So let us try to understand the details of that. And the company which has the product right now, like Lava, is trying to claim that they have tested this product for everything, and that's how you go on believing it. Correct? So why such kind of things are required? We will say it. Let us go in deep dive into this system on chip. This is a general schematic or general block of a SoC, right? If you take any SoC nowadays, it will have many things. Like for example, nowadays you will not find that there is an SoC and it works only on one central processing unit. Probably you might have more than one, many times, many more, because you say that it's a quad core processor, quad core, right? So that means multiple processors are present inside one single chip, which has been fabricated in a single process, in a single manufacturing process, correct? So there are multiple CPUs present. What else there is present on the any system on chip? There could be many interfaces. There could be many types of memories. Like for example, there will be an embedded memory. There could be a DDR RAM, correct? There are some SATA. There is a flash interface. So many things. Then there could be a graphics processor, because you need to your processor should be strong enough to differentiate, for example, color that was shown in the first video. Orange and red, one of the phone was able to detect, but another phone was showing same. So that means powerful graphics kind of processors, image processors. So here again you can see, and not only single processor, you could have a multiple graphics processors, right? For processing audio signals, you have an audio system, entire audio codec systems, correct? And there could be many interfaces like HDMI interface, PCI interface, general purpose ADC interface, touchscreen controllers, so on and so forth. So many things are there occupied on a system on chip. Just imagine a challenge to test the connectivity between different blocks. Forget about individual blocks, but the connectivity between these blocks. Because before fabrication itself, you have to have entire design of a system on chip ready, correct? So that is a challenge. So in this slide is to explain that there is a challenge for a testing or verification engineer, correct? Because many blocks are interlinked together, and they might be in fact from different domains, could be made available onto the same chip. This is a very generalized, typical. So this is a kind of a real life example. If you take a smartphone system on chip, like this is a chip from for a particular smartphone. So this chip is like an equivalent to a motherboard of a phone. You can call it as a motherboard. If you see, everything is present, like a motherboard has something, right? It is going to have a CPU, multi-core. It might be having a GPU, multi-core, image signal processors, video encoders, decoders, memories, caches. There are so many things present onto this system on chip, right? So now, if you see the uses of this system on chip, it can be used in any application. For example, let us say such kind of SoCs are used in automobile application. Now, where exactly these SoCs are present in automobile application? At many places, this is present in this automobile application. Correct? For example, it could be present inside the body and the chassis. For what purpose? The job of the SoC in this case probably could be automotive lighting, instrument cluster, steering mechanism, seating systems, door systems control, roof systems control, braking systems control. So there could be many things which are related to body and chassis, which are controlled by, right? Similarly, there could be system on chips present which are having safety and security features. For example, airbag, you can say, or classification, classification, etc. Immobilizers, so on and so forth. Blind spot warning, night vision systems, drivers, drowsiness assistance, park assistance, many things. There could be something related to the power, right? Like battery management system, DC to DC controllers, etc., engine management, etc. Along with all of these, nowadays, your cars are having, mostly they are having telematics and the infotainment systems, because cars have become very smart. So you can see in-car connectivity between different cars, right? Front and rear seat control, entertainment systems, driver information systems like GPS, etc., navigation systems, right? Remote vehicle interactions, telemetry. So there are so many things which needs to be controlled in single vehicle, and this job is done by system on chip. So when you try to design such kind of system on chip, basic design starts from a single small code, piece of a code, correct? Which you probably, let us say, download on FPGAs. Let us assume FPGAs before going for SoCs. So when you talk about FPGAs, does real FPGAs need verification? Because we anyway do the design of an RTL. We design the code. So simple example, yesterday he was trying to design the some multiplexer, decoder, multiplier, divider, right? Or some protocol. And then after once that design is done, then obviously he's going to do the simulation. Simulation is working fine. Then he generates a bit file. You generate a bit file and put it inside the FPGA, right? Obviously, FPGA is going to do its job and work as per your code. That's the meaning, right? Then what is the need of this new word, which is called as a verification? So let us talk about real life example. And there are so many examples if you Google out. This is one of the example. This is a particular FPGA from a company which has been shipped to the customers. And there were two fully customized FPGAs. Design was tested, properly done, everything has been carried out. But the verification of the design continues after the shipment of the product. Then they have found out, company has found out that there were 131 bugs found after 45 man weeks of verification. The product, which according to the company was supposed to be complete, right? Then they did a 10 man weeks of lab and at least identify more 9, right? While their statement, company's statement about the coverage was 100%. So this entire statistics reveals us a question mark, leaves us a question mark behind that. What's happening? A company is giving a product, and this product company says that 100% coverage, everything has been done, verified, simulated, basically all simulations carried out, testing carried out, but still there are bugs that have been identified. Correct? So there is something which is missing link and needs to be resolved. Correct? So now, first of all, let us talk about challenges in case of such kind of designs and such kind of verification environment. We will talk about what exactly the verification is, but before that, let us have a general aspect of what is the mean by verification and why we are doing that. This is one of the graph that tells you that there is a gap, and there is a serious gap between the designer and the manufacturer, and designer and the verification engineer. So there are, you can say, domains or engineers, you can say, are specified in the graph. One is the manufacturer or the people who are called as process engineers. They simply work on Moore's law. Moore's law, you know what is the meaning of Moore's law. So they work on this feature size of the Moore's law, and they are able to get this. They are able to get this. Correct? Every 18 to 24 months, they are able to double this transistor size. No issue in that. But then the challenge is with designer. Productivity of designer is not good as compared to the productivity of the manufacturing engineer, because how to use this? So many millions and billions of transistors are there, but how to use? So there's a gap that is called the designer's gap, right? Designer is not capable of, not capable of keeping the time closure with respect to the manufacturing engineer. So there is a gap, time gap, correct? Now let us consider a verification of the product. Now, if you see the verification of the product, this gap is further increased. This is much more. That means it has been manufactured, it is ready, but still there is a problem. There is a lot of verification gap. And this gap is very dangerous as far as we need to minimize this gap, correct? So therefore, we require the verification. Now let us talk about the market trend. What market says. This has been observed in the market that many a times there's a mismatch between the intent of the design and the actual specification that you get. For example, if there is a product application that needs to be designed, let us consider MP3. MP3 product. It's a kind of a audio application wherein, assume a simple case study kind of thing. Let us say I am the customer. I give an job to an engineer and I tell that I need a player when I'm going to hear the song, when I'm listening the song, parallelly I should be able to download the song and it should not stop the listening of my song. It should continue listening with a good quality audio, right? And I should be able to download, for example, as many as songs I want, maybe 100 songs. It should not stop, correct? That is my specification. I have given it to the designer. Designer delivers a product, but then at the end of the day, find that okay, I may not be able to download, or if at all I am able to download, some other issues may be there. Correct? Some other issues I don't want to have. Or let us say, even if the download isn't happening, probably it could be very slow. Only once or twice I am able to do that. And if downloading fails in between, I'm listening a song. Downloading is started. Downloading of the song is happening. I'm also listening the song, and suddenly there is a battery gone. Battery of the mobile phone or laptop, it has gone, and suddenly there is a shutdown. So now what? Correct. So these are the major issues, and this is one of the and this is one of the problem in case of industry, that there is a mismatch between the design intent of the design. The design is meant for what, and the actual specifications given by the designer, right? To talk about, and therefore that large increase in number of verification engineers. Yesterday also he was saying that if there are, let us say, for example, 4 designers are present in a company, then you require 6 verification engineers. In a broader term, around 70 to 80% are the verification engineers, and you can say 30 to 40% probably with the designers, right? Because my design should not fail at the end of the day. Now, with the increase in case of applications like AI, ML, data science, pervasive computing, so on and so forth, there is an increase in the data. There is a large increase in the data, correct? So my application become very complex. My entire design now become very complex. Now I need to deal with that complex also, correct? So these are challenges. There, a particular company needs entire resources, not only human resources, but their design time, money, etc. 70 to 80% goes into the verification. That means verification is a serious business. In short, verification is a serious business, and we need to understand what exactly verification. If I'm talking about the product, there is a mismatch that is happening in the product. If I'm talking about the recent development, then verification engineer has to cope up. There's a challenge. If I'm talking about the employment, then there's a big for the verification engineers. If I'm talking about the cost, time spent, it is a significant amount of time has been spent, a significant amount of cost needs to be spent. So therefore, I need to talk about, correct? In terms of this is a particular graph, in terms of cost of a bug, if you find out a bug in a product at a particular stage in the design of a product, then it is exponentially proportional to the cost. Means what? At product design cycle, when the product has been designed at the block level, initial stages, and you find out a bug into the product, probably cost of the product is very less. But when you go from the block level to subsystem design to system design to post silicon, and post silicon to the field. Now, if you product bug in the product, then Cost of finding of this bug will be very, very huge. You may need to recall your products back from the field, which is not so good idea. Correct? Therefore, what companies are doing, rather than paying attention to this part, they pay attention to this part, where cost of finding the bug is very small. So here latter part, system level, post-silicon level, you can say post-silicon and the field level is kind of a testing that you do. It's a testing. The word used is testing. After fabrication of the product, whatever you do is called as a testing. Before fabrication of the product, if you do, it is called as a verification. If you do means what? Verification means matching of the design intent with the actual specification, matching of the expectations with the specifications, matching of the functionality of the product that product gives than whatever is expected when you design the product. Correct? So that particular matching is actually a verification or is a testing. If I say my product should work like a simple AND gate, just a classroom example, AND gate. When I give inputs 0001 1011, it should work like an AND gate, right? So testing means after fabrication of the AND gate, I apply the inputs, I see the output, it is working fine, okay, it's not working fine, product is bad, rejected, correct? Lot of cost is involved because project is rejected after manufacturing. That is what is a testing. Verification means, okay, you want an AND gate, so I'm designing an AND gate, go on doing the verification of that product, whether it is giving me the desired specs. When I'm giving the input 00, what is the output? When I'm giving input 01, what is the output? Correct? This is called as a verification. Okay, so verification happens before the manufacturing of the product. Testing happens after the manufacturing of the product. So this is what we talked about just now. To match the design with the intent specs, unexpected behavior of the design we don't want. Therefore, we need verification. A lot of interaction happens nowadays between intellectual properties and the subsystems in a design, and therefore we need to think of the verification, because how do I match between the various designs, and cost of respins needs to be minimized. If you ask me, this is my personal opinion. It's not given in any book. This is my personal understanding that verification is carried out to build the confidence and stay in a business. That's it. If you verify the product, it gives you a confidence. Correct? If I'm doing anything, if I do a planning very well for my product, even this workshop, if I plan, it gives me a confidence that okay, my workshop will be conducted in a better manner. Correct? For a product also, there's a plan called the verification plan. There's a design plan. If I draft a plan properly and if I stick to the plan and everything goes very nicely, then probably it will give, as a designer or as a verification engineer or as a owner of the company, correct? It will give me a confidence that my product will be good. And therefore I can claim like a lava that, see, we have done all kinds of testing, and therefore you can procure or you can purchase the lava mobile. That was shown in that particular example or those videos, right? So it is about the confidence, to build the confidence and stay in the business, because I am sure that the company knows now that if I have a confidence of verification, that means my cost of respinning the product, which runs into millions of dollars, is going to be reduced. Correct? This is why we do the verification. So kind of a summary from the video till this particular point. Okay. Now this question, many times, even students in my class, when I teach verification, they do ask me, correct? Sir, वो तो सॉफ्टवेयर का काम है ना, syntax, you simply your software will find out if I let us say miss out the semicolon, what is the problem? Software will tell, when I'm writing a very long code, software will tell me that semicolon is missed. It will simply throw out an error. And if there's an error, I will rectify that. Okay. So what is the problem? Right? So my dear, it's not about the semicolon or anything. It is, we are talking about the functionality errors. Let us assume this as a code. This is a typical code, correct? In this particular code, if I miss out a semicolon somewhere, let us say here, if I miss out a semicolon, B000, 4-bit data it is, output is 4-bit data. If I miss it out in the coding, obviously when I'm going to compile, it will tell me that there is a semicolon required. But let us say if this case, now what is this case? This code is for like, there's a declaration of the state. State takes values 0, 1, 2, 3. It can take a value A particular state can be 0 state, 1 state, 2 state, or 3 state. So when it goes to an always, so it sees that what is the state at present. Depending on the state, it execute this case statement. What case statement says? See the state. What is the state? Is it 0? Then my output is going to be 0, 0, 0, 0. Is it 1? My output is going to be 0, 0, 0, 1. So expectation was when state is 0, output should be 0, 0. 4-bit output should come out 0, 0, 0, 0. When input state 1, output should be 0, 0, 0, 1. Input is 2, output should be 0, 0, 1, 0. And when input is 3, output should be 0, 1, 0, 0, 1, 1. But now what happens here, you see? The third case, when input is 3, output comes out to be 0, 1, 0, 0, which is not as expected. This is a kind of a logical error that has happened. And this example I am showing you so that you easily understand, right? So here we want 3, but somehow the designer, RTL designer has done a, let us say, typing mistake. It could be a logical mistake also. Rather than writing 0, 0, 1, 1, he has written is 0, 1, 0, 0. Now if I run this code, it is 100% sure that there you will not get a syntax error. There won't be any error. It will simulate also. Everything will be happen. But let us say whenever I am giving a stimulus in a test bench, whenever I am giving some input in a test, every time let us say this 0 comes or 1 comes or 2 comes, but this third case doesn't come. This third case doesn't come. Every time whenever I am simulating, I have not simulated for this case. That means I have designed this code. And then my code is perfect. There is no coding error, right? There is no error that has happened, no syntax error, nothing. Code coverage also, it will show kind of a good report. So everything has been done. Now what? Now when actually in a field, state goes to 3, it will come here and it will give the wrong output. It will give the wrong output, which is not expected. Therefore, I need a verification. It's not a simple syntactical check. It's not a simple syntactical check. That's what I want to say here, correct? So now, what is verification? And what verification engineer actually do? First of all, specifications are decided. Yes, specifications are there. So let us say designer is there. I want to design a MP3 product. MP3 product. So designer interprets the specs and then designer is going to write his own specifications. So designer creates the specifications which are called as design specs. Design specs which are called as design specs. Now, what from these specifications, designer is going to create a logic, RTL logic. And this what is your design, right? So designer takes the specs, interprets it, creates a design specs, and finally creates a logic. This is what designer does. What verification engineer does? To verification engineer also, the same specifications are given. So verification engineer interprets the specs. Then what verification engineer does? He prepares a plan which is called as a verification plan. He creates a plan. It's called as a verification plan. And verification engineer creates the test. Verifies, it creates multiple tests for the verification purpose. So verifier creates the test. Now, where is the bridge between these two? Because designer has created the design, verification engineer is ready with the plan, the test. Now, the matching between these two is being done, correct? So if there are any bugs that have been identified, needs to be communicated to the designer. Designer redesigns the circuit, again goes for the verification engineer, correct? So this is what is the flow for designer and this is the flow for verification engineer. So what exactly is the verification plan, correct? So plan means anything which you want to be successful. So you need to be prepared for that. If there's a goal, then there are stages. You start from stage 1, 2, 3, 4, 5, and that's how you can reach out to the end goal. So as far as verification is concerned, this entire design cycle and the verification cycle is concerned, this is what happens. First, any department in a company gets a requirement. They are called as marketing requirement. So they go on searching the market. Market is for what? What market wants. That is called as a marketing requirement. MRD, marketing requirement department. Then there is an architecture nowadays present in the companies. What they do is they prepare an architecture. So you get a specifications called as architectural specifications. From architectural specifications, you evolve the design specifications, and then you design an RTL. Correct? As soon as the design specs are ready, architecture specs are ready, your verification engineer comes into picture, and parallelly verification engineer goes on preparing the verification plan. Then this RTL has to be synthesized. So today's evening session, Kumar sir will show you the synthesis, etc. on Vivado toolset. Okay. So you can carry out the synthesis. Then you carry out the physical design. Finally, you carry out the timing analysis, and then you tape out the product. Now, in this entire cycle, which you are already aware of, we go from marketing department to the tape out of the product. Verification engineer has to work from start to end. Start to end, from the specs are decided till the product is stepped out. Verification engineer has no escape. Go through all these steps, and therefore the verification engineers are there. So now, what are the verification technology options available to us as an engineer? These are the various options available. These are kind of a basic keywords you can say in the domain of verification. They are called technologies. You can call them as static technologies. You can call them as formal verification technologies or physical verification and analysis. When you talk about simulation technologies, there are many simulators available. They are called as like event-based simulators, cycle-based simulators, transaction-based verification, code coverage analysis. So like today, he has opened one separate tool for code coverage, right? Then hardware software co-verifications, emulations-based systems, rapid prototyping systems, various hardware accelerators, particularly in case of audio video, you require the accelerators, and analog and mixed signal simulators. So there are many simulators nowadays available, and some of the simulators are very costly, and the training is also very costly. For example, event-based simulators are might be used in like embedded systems, right? Then there are technologies, they are called as static technologies. Static technologies means related to the lint checking. Oh, here arrow is somewhere wrong. This is blue arrow is formal technologies. Static technologies is second. Like lint checking. Lint means grammatical checking. Like I said, semicolon is missed. Somewhere full stop is required, that is missed, right? Colon is required, that is missed, right? Or keyword, some misspelled. So lint kind of a checking, and the timing verification. And here working on the STA or timing verification part, they are working on static technologies. And then there are formal verifications. That means the people who are working on proving the model, equivalence models. You know the De Morgan's theorem, right? So this works on those basic principles like De Morgan's theorems, equivalence checking, model checking, etc. And you have a physical verification of the physical verification and the analysis of the I will ask here whether ending or it makes a sense, and then I will go to next slide. So in chat box you have mentioned anything? Nothing, because I'm not able to see the chat box now. Okay, any questions up to this point? I introduced why verification is required. That's it. We have not done any verification as such. Any problem? Anything? Issues. Okay. So now go ahead. Came out. Okay. Now next point comes how to verify design. Now we go to the verification, right? How to verify the design. This is your physical laboratory setup that is present in any department, electronics department generally. What it carries out? It carries out a test bench. This is called as a test bench. Test bench means what? It have testing equipments. It could have arbitrary function generator or CRO, etc., etc. All these kind of equipments, right? It is a bench on which you put these equipments. Then you have something which is called as a design under test. So this is your design under test, a design which you would like to test, right? Now what you do is you apply the input to this design under test and you collect the responses. What you do in physics. laboratory also. You put here some circuit that you design. It could be an amplifier or it could be anything. Then you apply the input signals and you collect the responses on the CRO. And that's how you say that your design is being manual. This is what is the test bench. So in yesterday's session or day before yesterday's session, he was actually designing the code. He was actually designing the RTL. That's it. Correct? So what exactly the test bench is then? So the job of the test bench is to apply the stimulus and to collect the responses. Right? If test bench is doing only this much, applying the inputs, collecting the applying the inputs, collecting the responses, then that's the very preliminary kind of a test bench. And nowadays, designs are so complex that you require a smart test bench. We require everything smart, like mobile smart, everything smart. Similarly, our test benches needs to be very smart. What do I mean by smartness in the test bench? For example, here it is shown self-checking test bench. That means if I apply the input to the design and the test, I get the response. I don't want to see the response. I don't want to check because it's not possible for me. I have shown you some of the FPGA or those designs, SOC designs you can see, so complex. That was the intention of showing that design, that it is so complex that I cannot see by naked eye each and every signal. I cannot go each and every signal that whether it's correct or not. Correct? It's not possible. Therefore, my test bench needs to be smart. So what I do is I store an expected response and I compare this actual response with the expected response and I get a result. That's it. So these are the test benches which are called as self-checking test benches. So what self-test bench does? It actually takes the input. It gives the input to the DUT. It collects the responses from the DUT. And there is a golden model or reference model which is already present inside the test bench, which generates the expected responses. And these expected responses are compared with the actual responses. And that's how finally, as a verification engineer, you will come to know that how your design is behaving. Okay. So we have a concept of self-checking test benches. So I will go more into details of this self-checking test bench. Nowadays, the layered test benches. So they are called as layered test bench. You can see how the design of the test bench is carried out. Correct? So in this test bench, you have a design under test, which is at the bottom level, which is given by the designer, and it is an RTL. So this is the job of the designer, which is called as a DUT, which you get from the designer, right? What verification engineer does, prepares a plan and everything, and verification engineer has to ready with this layered test bench. To be ready with the test bench. So what do you mean by readiness of the verification engineer here? So here this entire layered test bench is divided into multiple layers. Bottom layer is called as a signal layer. On top of that, there's a command layer. On top of the functional layer, and on top of that, there's a scenario. Right? I will go from bottom to up, and then we will come from top to bottom. Let us say I want to test the DUT. Some design, MP3 player is to be tested. Design of MP3 player. So basically, I need to give some inputs and I need to collect outputs. Correct? So in RTL, I will have many inputs, hundreds will be there. Correct? Including clock, there may be some data bus, there may be some address bus. There are so many signals. So these signals needs to be generated, and they are the low level signal, lowest level signals. Correct? So there is a block present in the higher level. There's a command level. The job of this driver is to give out the lower level signals to the design under test. Driver will give out the lowest level signals to the design under test, applied to the design under test. Then DUT will give the response, and response is collected by a block called as a monitor. So lowest level is a signal level in which actual signals are present and they are applied to the DUT. On top of that, there is a command layer which consists of multiple blocks. So first, let the monitor block, accessions will see later. The driver's job is to convert the commands from the functional or the agent to the lower level signals. So on top of that, there is the agent which gives out the command. The driver, right? This functional block also has a unit called as a checker. What is the job of the checker? What this monitor is? Monitor simply monitors the response. Monitor simply looks out for what is the actual output. continuously monitoring of the output of the DUT is being carried out, and this output, which is present in the lowest form, is given to the checker. Suitable conversion will be carried out and it is being given to the checker. On top of command block or command layer, there is a layer that's called a functional layer. What functional layer it does? In functional layer, you have an agent, you have a scoreboard, you have a checker. What agent does? Of the agent is to convert a particular scenario, commands, a particular scene into the commands, right? So agent lies between a generator and a driver. Agent gets the particular scene, agent sees the scene, and those commands being given to the driver, right? Agent does the two jobs. One is to communicate to the driver, another is to actually store the correct response into the scoreboard. Scoreboard is like a kind of a, in games, we use a scoreboard for maintaining the score, like that. So agent gives the output to the scoreboard. What checker will do? Checker will take the output of the scoreboard and it will capture responses, it will compare the responses, and it will give out the output for the verification or the coverage, functional coverage, you can say. On top of this functional layer, you have a layer called a scenario layer. What scenario does? Scenario layer creates multiple scenarios, many scenarios. So there is a block called as a generator block, which will create scenarios, correct? And this entire layer or the entire test bench, this is called as an environment in case of a test bench. So this is an environment block, right? And on top of this, there is a test vectors that you get. Now I will go from top to bottom. Let us assume your MP3 as a product. MP3 player, I design RTL given by the designer. RTL is present with me. Now I have to create multiple tests. So when I decide the test to be carried out, I have to first create an environment. What environment is? Environment contains multiple blocks. First block is a generator. What generator does? It creates multiple scenarios. What do you mean by scenario? Scenario number one. Scenario number one is I should be able to play the song. That's it. Scenario number two, I should be able to play the song, or let us say I should be able to play the song. Let us say scenario 2 is I should be able to download the song. Scenario number 3 is one, be able to download the song. Scenario number 4 is I should be able to adjust the volume to so and so level. Scenario number 5 is I should be able to adjust what example MP3 player, any feature, any specifications you can take, any particular feature. Correct. Scenario 5 is if there is a last scenario is let us say there is a battery failure. Suddenly power shut down, my MP3 goes off. Now what happens? After that, what happens? So when the reset is being done, resetting of the product is being done, then what kind of scene is being created? Whether my MP3 player will start playing of the song, the point at which it has been stopped, or it will restart from the origin, or it is not going to do anything. Let us say downloading stops in between or it is paused. Then what happens? The scenario. Then what happens? When the downloading stops, battery fails, everything happens, I restart. When reset is being done, now what happens to the downloading? Will it continue the downloading of the rest of the song, or it will simply come out of that downloading? Correct? Or what? What else? Or it simply breaks the product. These are the various scenarios which needs to be generated, and this is the job of a generator. Once this scene is decided, for example, I need to play the song, it's the scene. Now I have to go for actually creation of various functions, right? And these are being done by your agent. What agent does? Agent actually creates this scene, converts this scene into the actual commands, interpreting all functions, correct? So this is what is the job of agent. And agent also maintains all the specs or all the expected outputs inside the scoreboard. You convert the scene into the proper commands. Those commands are converted into the lower level signals, zeros and ones by the driver, and they are applied to the DUT. Monitor collect the responses. Checker goes on checking the expected response, and that's how you get it. In monitor continuously function of the design and the test, you would like to monitor particularly warnings, errors, etc. if at all they are present or not. So there is a concept called as assertions. Assertions is a block again present in command. It continuously monitors the intermediate functionality of the design and the test. This is what is a layered test bench. This is the concept of a layered test bench. This one figure, this one is enough for one entire course, to teach one entire course on the verification. Because how to create the generator, how to create the agent, how to create the scoreboard, lots and lots of lines of a code you have to write for completing the test bench, right? So now I have explained you first what is the motivation. Then I have explained you what do you mean by bench exactly, first in the position of the verification engineer. Now I would like to create this test bench. What is the language that is present to me? There are many system level languages present. For example, there is a Java, there is a Superlog, and there are so many languages present, correct? Including your VHDL Verilog, called as a system Verilog, or there was a handle C, etc. C++ based handle C, SOC++. There are so many languages, correct? Out of that, we go for system Verilog, right? And why we go for Verilog? So this slide will tell you why we go for system Verilog. Initially, there was a Verilog extensions. Primarily, the major extensions were carried out in Verilog 2001. Verilog 2001 was a very standard, and then 2007 also came, and then finally, around 2010, it was renamed as a system Verilog, and then the just stick to system Verilog. But in an industry, people use two different terminologies. One is Verilog, another is system Verilog. Verilog is used by the designers. For example, MP3 product design has to be created. So who is going to create that? Designer is going to create that. Okay. Now, when verification engineer works, verification engineer requires a different kind of EDA or I would say EDA toolset. Verification engineer requires different kind of toolset. What do I mean by different kind of toolset? Verification engineer requires a generator which is going to generate a lot of scenarios, which designer does not require, correct? Because designer sees that, okay, this is the design specification, I got it, done. But if there are so many kinds of errors are going to happen, I'm not going to test all those things, right? That designer is not going to do. So that is to be done by verification engineer. I require a software or I require a language which has many capabilities which are going to help me as a verification engineer. So what are the capabilities I need? These are the capabilities I need as a verification engineer, which are shown on this particular slide. I require the test benches, powerful test benches to be written. I should be capable of writing powerful test benches in system Verilog. What do I mean by powerful test benches? I should be able to model the system, entire system. I should be able to use the object-oriented programming kind of concepts because those concepts are very good. I can reuse them in my verification environment. I should be able to randomize my constraints. Then only this should happen. That kind of thing. I should be able to randomize my constraint. I should know how much of code has been covered. All these functionalities are required. Test bench related functionalities are required, and these functionalities are given by the system Verilog. They are available in system Verilog, and therefore I can go for system Verilog. Next is advanced design-based concepts. If at all I need, yes, they are present. Basic Verilog constructs or Verilog constructs are present in the system Verilog also, right? So there is no question that this is there in Verilog and this is not there in Verilog. So in system Verilog is an extension of Verilog. It's an extension kind of thing. So enhanced design constructs are available for hardware modeling actually. Then there are many other things like system assertions. There are features like properties, capture property, capture behavior, all these things, capture assumptions, covers. So in short, I will talk about assertions also on one or the other slide. And then there are features that are required for me, which is called as a DPI, direct programming interface. I need to interface my system Verilog language to other languages. For example, C++. I want an interfacing between C++ to system Verilog. Can I do that? That you can't do in Verilog, correct? You can't have C++ program and then talking to the Verilog program. But in system Verilog, you can have handshaking between C++ and the system Verilog program. Because there are many functions, for example, DSP functions, etc., which are already written in C++. I can reuse them if I get that functionality. And that is available in system Verilog. So these are very powerful features of system Verilog, and therefore I can go for system Verilog. Now let us try to understand few features. So I'm going to now onwards about these features only. That's it, nothing else. Okay. Now I will give you the highlight of these features, and then I will open the toolset and I will show you few examples. Now some of the differentiating features that I will speak. So in last 2 days, you might have encountered this word many a times, wire and reg. I really don't know how many of you are clear about what is wire and what is reg. Correct? And to avoid that confusion, System Verilog has come up with new data type, which is called as logic. What is the difference between wire and reg? And here logic. So forget about wire and reg now. Correct? Wire means it will not store any data, nothing comes and goes away. And reg means you have the so there's a difference. But let us say I am confused in wire and reg. No problem. System Verilog introduces a new logic type. Since wire and reg is called as a 4-value system. It's a 4-value system. What do you mean by 4-value system? It can take 4 values. It can take 0. It can take 1. It can take X. X means don't care. Or it can take Z. Z means trash state. These 4 values are possible. 0, 1, X and Z. That is possible in Verilog. Correct? Here, System Verilog has introduced a new data type which is called as logic, which is also a 4-value based system. That means now in this example, if I'm writing logic reset, I don't know how to, whether this reset is wire or reg, how to declare, I'm confused. So I simply write it as a logic. It means, but I'm sure that reset could be 0, reset could be don't know, don't care, it could be trash stated. Then I declare it as a logic. Okay? I can have a bus like data bus 16-bit logic data type. So this is a differentiating factor from the Verilog programming language. In System Verilog, you do have the different kinds of a logic data type. There are so many data types present in System Verilog. So just an explanation of logic and the bit type, because this is quite interesting and important also. There is an enhanced present in case of System Verilog, which is called as a 2-state data type. So logic is a 4-state, bit is a 2-state, which is present in Verilog. Here differentiating logic and the bit. Bit take only 0 and 1. You cannot give X and Z to the bit. Bit will take only 0 and 1. This has been carried out. Why in System Verilog bit kind of logic data type has been worked out? Because of multiple reasons. One of the reason is a potential reduction in the memory. When I store the X and Z, it takes a lot of memory rather than zeros and ones, right? So my reduction in the memory, runtime improvements, this is my benefit, potential memory and the runtime improvement I get in 2-state data type. High level modeling benefits I get if the model is at a high level, for example, C++ model. In C++, you have price stated impedances and X, don't care this kind of concepts. You can have 0 and 1 in C++, but you don't have X and Z, right? So therefore, but I want to take the benefit of that. So therefore, we have high level models. Modeling concepts directly to be imported here. So we require 2-state data types. Okay. So that's the purpose. So basically to avoid all this kind of confusion, we have a bit data type. These are the bit data types. In System Verilog, we have bit is a single bit, byte is an 8-bit, short int is a 16-bit, int is a 32-bit, and long int is a 64-bit. So 1, 2, 4, 8, 64. So types are available. Other than these, your regular int and all data types like arrays, fixed arrays, all those kind of things are present. Enumerations, all those things are there in System Verilog present, right? So now let us say I would like to write a first System Verilog program. This is a simple design of a full bit adder, right? Full adder. So A, B, C in inputs, and S is the outputs. Out is the carry out. So this is my design. Write a RTL code. Yesterday he has written the code for this, and then once you design an RTL, you download it into FPGA and you assume that it's working properly. Correct? Verification engineer has to do a lot of things, even if you want to design the simple this thing. But I will show you a smaller code at least how to write in a System Verilog. Now from this one bit full adder, you can design any chain, any kind of a adder. For example, this is a 0, 1, 2, 3, 4, 4-bit, 0, 1, 2, 3, 4, 8-bit adder, right? Up to 7. So it is a full adder kind of a chain. Once designed, then you can have any data like this. For example, this is 170 plus 51 given to the chain, and you are getting 221 as the output, right? This is what you want. This is what you want. So hierarchical follow. You can design single full bit adder, then you can go on combining using different approaches. It could be a carry save adder or whatever kind of adders data part design you study, you can implement that. Just as an example. This particular code over here, this particular code over here, right? So this is the adder that is expected. This is about the system Verilog code. It is not a complete verification code. It's how the code will look like in system Verilog. So it's an extension of Verilog. Therefore, it looks like a Verilog. So here you require a adder which adds 8 bits. So these are the 2 bits, 2 inputs. A is an 8-bit input. B is also an 8-bit input. Since it's a full adder, I require a carry in. Then obviously there will be a carry out and sum. So here you have to give a module name. Module is the keyword. You give a module name like some adder here. In bracket, you write down the sensitivity list. Whatever input output ports are there, that port list you can write. Separately, you have to declare all these ports. Out of this, which are input, which are output. So input is A and B. Cin is the again input. Outputs are sum and Cout. These are the outputs. I don't know reg, int, etc. I write simply logic. Okay, logic is a data type. It can take any value 0, 1, etc., etc., x and z. If I require any intermediate signal, I can also write intermediate signal. For example, I require the result to be stored. Some intermediate signals are going from here and there. I require those signals. So let us say result. And now I simply need an addition, one of the kind of modeling style. There could be many. Let us say one of the style. I simply add A plus B and result is there available with me with an assign statement. So I'm inferring an assign statement. Whenever I use an assign statement, the meaning is it generates a combinational logic. It generates a combinational logic, right? And then this result will be stored into some sum. And finally, 8th of the result, I can see out, correct? So 8 bits into sum and last 8th bit, or you can say 9th bit, whatever you want. It is a carryout. This is a C out. So this is the description of the functionality. So code looks exactly similar to the Verilog, but you will see the differences in case of this, in this example, in terms of data type. That's it, right? So now I will go to concepts by telling you this thing. I will go to these concepts which are shown over here one by one. Just the meaning of these concepts. We cannot implement, but then you should understand at least keywords. First of all, there is a keyword called as interfaces that is present in case of system Verilog. What do I mean by interface? There are interfaces present. Let us consider this example. This is the design under test. It's a particular system from a microcomputer system, you can say, from a particular design. Some block arbiter has to be tested. So what's the job of arbiter? Job of arbiter is to do the arbitration between various you can say lines, maybe data line, address line, etc., etc. So it does the arbitration. Let us assume that there are some signals to this arbiter. There is a signal called as reset. Arbiter has to be reset. There is a signal called as clock. When arbiter gets a request, it has to see whether he can allow the access or not. If arbiter is ready to give the access to, let us say, some resource, then arbiter will grant the access. For example, there are multiple blocks present in a system. Those blocks, they want the use of data bus. There are 2 blocks, both want the use of data bus. So request comes over here. Once arbiter gets a request, arbiter will look and then grant the access to a particular block. So you can see that there are 2 requests, 2 input requests, and 2 signals, you can say, right? This is what is the design over here, and these are the signals. It is a very simple example. But just now consider that this is not an arbiter and it's a kind of some other different block. It's a big block. How many signals will be there? There will be many signals. There will be many signals present around this arbiter. Correct? I need to connect as a verification engineer, each and every signal from this arbiter to the test bench. Signal, I have to be very, very careful in writing their names, right, and connecting them properly to the design under test. I should be taking output also properly. And if there is a flow like loop inside loop, then I will be simply confused. Again, if there is a multi-team environment, for example, one team in a company, one team is working on some concept, second is working on some concept, third is working, and there is a project leader of all those teams. Now, project leader will get a design from team number 1, they design from team number 2, they design from team number 3. He has to combine and finally create a product. He will be simply confused if, let us say, a designer uses, for example, same name. ABC is the name given by one of the designer in a particular parameter. Second designer also has used the same ABC name. Third, because that may happen, correct? That is going to happen. Now, what this leader will do? There is a problem, right? So to avoid all such kind of problems, there is a concept called as interfaces. There is a concept called as interfaces. So what do you mean by interfaces? In short, so this is another example here. This is a design under test. This is a test bench. And now test bench gives out some data. Design under test gives out some address. That means DUT will give the address. This will give the data. There's an enable, read. All this kind of handshaking is happening. Right? This is a normal way of writing a program or system Verilog program. This might become very complex in interfacing of the two blocks. So System Verilog has introduced a concept of interfaces. What you can do is you can write a separate code in System Verilog. It's a code. Interface is a code. You write a separate code in System Verilog, which will actually do the job of all these lines. Basically, these lines, what are these lines? These lines are nothing but connections between different blocks. However, these connections are not simple wires. They are not simple wires. They are intelligent signals. They have a meaning. They are meaningful signals. For example, if I write enable signal here and there's a direction to this signal, it should go from DUT to the test bench. You cannot have in a reverse direction, correct? Similarly, enable signal means what? It could carry a particular information. It could be 1 or 0, let us say, right? These are all intelligent signals. Okay, so interface is a bundle of intelligent signals. They are not simply wires. This is one aspect in case of intelligent interfaces. Second aspect, as far as interfaces are concerned, second aspect is in my entire system on chip, I may require at many places. For example, it is between these two blocks. I have shown you how complex the system on chip is nowadays. There are so many blocks present on one SoC. Same signals I may require at other place also. So mapping of one-to-one pin becomes very difficult for verification engineer. So what it does is he actually combines all this, creates an interface, and then he simply goes on connecting this interface as various places. So writing the interfaces itself is a job, separate job, writing the interfaces, correct? You can go on writing the interfaces. One more point. Intelligent means what? For example, there could be a clocking information, right? There could be a protocol related information. If let us say data exchange doesn't happen properly, who is going to tell me, DUT or test bench? Your interface itself can tell us that there is a violation of the particular protocol, right? Or there could be some parity introduced into the interface, parity bit. So those kind of things are possible. That is called as an interfaces. Next word you might have heard, which is called as a randomization. So what do you mean by randomization? Randomization is used in a testing. Let us say I want to test here. This circle shows there are many testing points. I simply go on shooting with the gun. Then it may strike here, anywhere. I don't know where. Randomly. Correct? Completely random. Which is there in Verilog also. In fact, there is a random word also. That is what he was trying to tell yesterday and day before yesterday. Verilog mein random hota hai. That's what he was trying. You can put some, but that randomization is like this. This is what is going to happen. What do you want? You want like this. Center. You want to hit the center. Correct? So this to this one is possible in System Verilog. So in System Verilog, randomization is there, but it is called as a constrained randomization. The word uses a constraint. You provide the constraints. I want to hit exactly this feature of the design. That is possible in case of System Verilog. So that is what is shown over here. What is randomization? Randomization is covering the untested areas. Untested areas, some of the features in a design which are never going to be tested, which are never going to be seen. That is possible in case of randomization. You can tight the constraint. It is possible to create the tighter constraints in case of randomization. Correct? For example, let us say there are multiple ports in a chip. There are IO ports. IO port 1, IO port 2, IO port 3, IO port 4. And designer has created a design 4-port chip and given to you. This is my chip and it is having 4 ports. 8-bit 4 ports are there. Now, if he has not tested all ports properly, and if they are bidirectional ports, so that means all are able to transmit the data, all should be able to receive the data, that kind of thing.
राठोड सर सर चालू झालंय
हो तेच बरोबर माहिती आहे मला तेच ठीक आहे प्लीज त्याच्या बाहेर त्यांनी मलाच बाहेर करून टाकलं Okay, my screen is visible again because I have to show now software. Right? My screen is visible or not? कोई तो एक जल्दी.
विजिबल है सर.
Okay. So this is about the coverages like toggle coverage, path coverage. So basically, when I talk about coverage means it's a statement related, block related, which part of the code has been executed or not. That is a coverage. And when we say functional coverage, this is important. This is something different. What is functional coverage? For example, here, if I say that is the first in first out code is there, is it executed properly? Or is it still empty? First in first out. एक FIFO queue है हमारे पास. Whether that queue is empty or it is full, I would like to know that. Correct? So such kind of functions, like all the FIFOs are filled completely. Read and write operations are performed completely. How the packets with the suitable lengths are allowed. For example, I want to transmit, let us say, 32-bit of a packet. And I am trying to transfer 64-bit of a packet. And it is not allowed by my design. So, what is happening? Did the DUT got verified with the packets? Did the monitor observe all the results? All these kind of things are nothing but functional coverage. Okay. So, we don't have time to talk about coverage, etc. So otherwise I would have told you, but then the last thing I'll tell you about the assertions. What is assertions? Assertions means it is not a new concept. It's a very old concept. It is present, in fact, in many things like Java programming, BHDL. Also, there was an assert. But what is the concept? Concept is like this. In system very log, you have such kind of statements available, like assert property at positive edge of clock A and B. What does it mean? If there is a design, it has got a property that if there is a positive edge of the clock, in that case, A and B both should be 1. A and B has to be asserted or it should be activated. Let us assume it should be activated. If it is not activated at the positive edge of the clock, it's an error in the design, right? So I write a statement like this. One statement is enough for me. That is assert property. It's called a property. It's a statement, keyword in system Verilog. Assert a property of my design. What is the property? Property is that if there is a positivity of the clock A and B, it's a declarative statement. System Verilog assertions is a declarative language. So I write it this way. This is the actual code. All at the rate positive of the clock begin if like this, then assertion failed. This is the actual code in Verilog, right? It could be in system Verilog also. But if I want to check whether this property has been satisfied or not, if there is an error, A and B is not equal to 1, it is, if this becomes successful here, this bracket condition becomes successful, it should give me error like assertion failed, right? I can do that by using an assert property. So assertions are also available in case of system Verilog. And we need assertion for verifying a complex design. Like this, there may be many blocks present. I am simulating these blocks. So I get a lot of waveforms. Very difficult to identify all these waveforms, correct? For example, if there's a clock tick, then this should come, select line should come. If there's a select line, then this clock should be 1. If this clock is 1, then there has to be a reset in the counter. If there's a reset in the counter, then this should be the output. See, how many times I can go on verifying like this? Very difficult. It's a big complex design. Assume that my engineer in my team, there are 10 engineers present, everybody has verified. But as a project leader, how do I know everybody has verified properly? So we require the help of assertions and the coverages. This is the purpose of assertions and the coverage. Okay. This is the last slide, which tells you if it is a verification. I have explained you all keywords in case of system Verilog and the Verilog. New things, something which is new, correct? If somebody wants to become a verification engineer, what is the skill set required? Number 1, digital design and computer architecture concept should be very clear. Verilog or VHDL programming concept should be very clear. Next is system Verilog fundamentals, somebody should know. Then the concept of randomization. Fundamentals means only like data type, etc., all those. The way you study Verilog programming. If you study in the same way system Verilog programming, they are called as system Verilog fundamentals. But if you study system Verilog in a different manner, like I want to do the randomization, I want to do the coverage, I want to do the assertions, then that's the next thing. Tools for various kinds of tools for debug experience, and finally, kind of thing called as a methodology, verification methodologies, etc. So this is the tool set. This is the skill set that is required by a verification engineer, and somebody having this particular profile, starting from digital design to a UVM. I don't think that particular candidate will have any problem in case of, at least nowadays, in case of job, right? So this is about basics of system Verilog. Now what I can do is I will go to the software and I will open fast. Somebody should say that you can see my this thing browser. Yes or no? Now pay attention. We will execute few codes in 10 minutes, but I will show you the methodology. Can you see the browser? Any one person? Yes or no? If not, I will stop sharing. I will reshare. But I can't see. I can't hear voice from a single person.
Yes, sir. Yes, sir. We can see. You can see, sir.
So I don't know why there is no response. If you are not interested, I can stop also. Huh? There is no point. आपको लग रहा होगा कि सर बता रहे, but I think this is important. That's why I'm taking it. And I got an opportunity to explain. ये जो अभी मैं बताने वाला हूँ, कल का प्लान था कि ये इतना ही लैब का बताने का, but I have extended because I thought कि these are good concepts and we don't have any session on this. So let me take it. So now I will take you to tool set. I don't know whether you are aware or not. Have you heard of EDA Playground? EDA Playground कितने लोगों ने सुना है? Yes and no. Anybody? EDA Playground. Have you heard of EDA Playground? I'll write here. EDA. इसके बारे में सुना है? No. Okay. Then that means these 10 minutes will be very valuable for you. Please pay attention. You don't require any other software for doing this Verilog system Verilog studying, nothing. It is available on your phone. So now, just see. Where is that one? It has directly come. Because I accessed it. See, what you do is, you can see my screen, I suppose. You type EDA playground here. Afterwards, you can try it out. Okay. You can see the screen, right? You can type EDA playground.
सर
हा
सर तुम्ही स्क्रीन शेअर केली आहे का?
मी मगापासून तेच तर 10 वेळा विचारलं सगळ्यांना. Nobody is
नाही
answering.
नाही नो सर युअर स्क्रीन इज नॉट देअर.
That is what I was asking to everyone. Can you see my browser? Can you see my browser? So nobody has replied.
No sir, actually I was checking on YouTube, that's why I
Okay.
became late. Yeah, your screen is not visible, sir.
नाही मी पार्टिसिपंट कडनं तो मी एक्सपेक्टेड करतो ना 22 आर देयर at least.
Hello. Sir, at starting it was visible, but now it is not visible, sir.
Okay. So you please tell me, no, because I see now the problem is I am having the host control at the same time I am presenter. So multitasking is happening on my laptop now. So
yes, couple of people interacted with you, but you are not able to hear. I think so.
Acha. Okay. But now you tell me, is it visible?
Yes, now it is visible.
Now,
Yes.
madam, you one of you remain unmuted. I request, please. One of you who can give me feedback in between. See, we type EDA playground. Okay. See, I simply type EDA playground here in Google, and I can go to login. Okay, you can create your login separately afterwards, and once you create login, you will be able to access it. Directly going here. It is going directly here. Okay. Now you can see the window, right?
Yes, sir.
Sir, you keep remain unmuted, please. Now in this window, this is the software online available to you on your mobile platform, everything. Which languages you can do the simulation? I'll click and I will show you here. See, if I click this left-hand side, you can do the simulation of all these: VHDL, System Verilog, SPECman, Python, C++, Perl, all these things. Our intention is System Verilog, so I select System Verilog. You can use methodologies, forget about that. That's out of scope of our course now. Libraries, etc. Tools and simulators. Which softwares I want to use? Okay, I come here and I select. There are commercial softwares which are freely available onto this site. Which are those? Riviera from Aldex. Axelium from Xilinx. Cadence. Questasim from Mentor Graphics. VCS Synopsys. All these are there. Compilers are there. Okay. So I select any one of that. Let us say Cadence. We will go for Cadence itself. Cadence Xilinx. Now I can select here whether I want to see the waveform or not. If I want to see the waveform, I have to make sure that I click this. I keep it clicked. Open EPWave, right? And then if you see this side, there are two windows. One is a test bench. Another is design. Testbench.sv, design.sv. I can write a design. I can write a test bench. I can simulate. At bottom side, there is a window, right? It is a command kind of things that you will get. Now here there is to save your data or your code. You can save it. You can make it publish. You can make it public. You can make it private. You can share it on various groups. All those things are possible here. I will execute first, let us say, Verilog code. There are many ready-made examples available for execute. VHDL, Verilog, etc. Let us go for Verilog. Simple example first, right? So I click on this Verilog system Verilog. Correct? Let us say, so many examples have come. Default many examples are there. Let us say I want to simulate a D flip-flop. I simulate a D flip-flop, ready-made example, okay? See, this is the example for D flip-flop. You can write your own code of D flip-flop. So this is a design wherein you can enter the design of D flip-flop. This is a test bench wherein you can enter the test bench for D flip-flop. So what are the input outputs of D flip-flop? These are all input outputs: clock, reset, D, Q, Q bar, etc. So you can understand what is D flip-flop. So always at the rate of positive edge of the clock, if reset is there, 0 should be assigned to Q, else D should be assigned to Q, like that. What is test bench? Now I am giving different conditions in the test bench. So there is a module test. There is a D flip-flop instantiation. It has been instantiated, right? So syntax you learn afterwards. Various cases like reset the flip-flop means clock equal to 0, reset should be 1, D should be X, display. All these things I do. This is a test bench. Now next question is, okay, sir, we have selected this, return the design, return the test bench, how to run? There's a command here, there's a tick, run button is there. I simply run it and see what happens. So code is run, done, right? Simulation has finished, but nothing is visible. Why? Waveform, I have it has see all textual form has come. Let me see this left hand side. Tools and simulators, examples. Open VPO. Where is the open VPO?
Tools.
It was disabled. Okay. There is an option, open EPView. It has run successfully. You can read this resetting, etc. happened. But I would like to show you in case of waveforms. So I click this. I'll rerun now. Now the waveform window will open. Can you see the waveform window?
Yes, sir.
Yes.
Yes, sir.
Yes. Yes. Now you can zoom it. You can see. So you can see that there's a clock, there's a D, there's a Q, Q bar, reset. All these things. It is a freely available software. Correct? Everything is freely available. It is a EDA playground. Now I will show you a system Verilog code, but my code. Okay. So I am using this software not started now, but last for probably 5, 6, 7 years. So I will show my any one of the code which I have written. There are many codes. What do I show? Let's say yesterday's example, blocking and non-blocking statement. The reason I'm picking that because I have seen the responses in quiz that you have attempted, and I feel that blocking and non-blocking is still not clear. Okay, directly it is there. Verification blocking statement. Let me see how many blocking related programs. At least 1 or 2 will be there. Okay. So these are the various programs which I had written earlier. So I will open one of the program. In short, I will explain you difference between blocking and non-blocking, and this is the system Verilog code. Okay. Now here, this language selected is system Verilog or Verilog, same interface, no difference. Correct. Here, let us execute directly test bench. System Verilog, when you talk, RTL, if it is there, has to be towards right hand side design, left hand side, this is a test bench. We are working only on verification. We need not worry about design aspects right now. So my code is written in this manner. What is the code? Let me explain in short. Let me see first. There are A, B, C, D, E inputs, let us say. If now in this case, A is equal to A, display the values A, B, C. A is assigned to B, means B is given to B. Then what is ABC? CC is given to C. What is ABC? There is one initial block and then there is another initial block, right? Wherein I am initializing the values here to A first, then B, then C, then here D, and then E. If I go on executing this sequence, first of all, anyone, can you tell me this is a blocking, non-blocking? Anybody remembers?
Blocking, sir.
Blocking, because equal. Blocking means immediate assignment will be there, right? Immediate assignment is going to be there. It is not going to wait. So I am going to run it. So I'll run it and you can see the results. Okay, running is done. It's done now. Now you can see here, I hope you are able to see Xcelium, cadence toolset. Xcelium is the next version of what we have studied actually. In CView, uske baad Xcelium is the latest one available with us. So Xcelium is there, we run it. Now here, see first statement has got executed, A display is here. Display ABC, A is A. So you can see here what is displayed. It is AA, XX, XX. Means AA is changed. When B is changed, next display statement comes. It should display A and B. Whether it is displaying, yes, it is displaying A and B. When third CC comes, it is displaying ABCC. So properly immediate assignment is being carried out, right? In following block also, like second initial also, it is being done. DDEE assigned. Now let us go for another statement, another example of non-blocking. If we simply replace it by non-blocking, what happens? So I definitely have similar example. Blocking is there, then non-blocking will be there, yes. But example, same example open. So that I need not go on doing the changes in the code. Non-blocking one. Yes, yes, it is non-blocking. Yeah, you can see this is a non-blocking code. It is exactly same, right? Now, interesting thing you can study. Run this, you will not get the same answer. So what do you understand by non-blocking? Non-blocking is related to the time instance. So if they, now here in this code, you can see there is no timing parameter mentioned, no timing, nothing. And therefore, all these statements will execute in a single instance of time. Time cycle will not progress. There is no timing parameter mentioned. There is no delay. Therefore, all statements, all assignments will be executed in a single instance of time. It will not block the execution. Therefore, any one of you can tell me what will be the value of A, B, B, C, C, D, D shown over here after the simulation is run. मैं बताता हूँ. It has to be X. No, it will not be A, B. When it come, it will not come. See, it has to be X. All don't care. No value will be assigned. Non-blocking statement. A, B, C, all cases. It is only XX. This is the difference. Why? Because it comes here. A has to be assigned to A. Correct? It takes this A, but actual assignment happens at the end of execution of this. Therefore, actually assigned clock has not incremented. If there's a clock, there probably would be a different result. Now that I will show you if there's a timing parameter, how the result is going to be. That also I can show you immediately. So non-blocking, I will go to non-blocking, search, second code of non-blocking. In this codes looks exactly same, but timing parameters are inserted. You can see that how the timing is. After 10, let us say nano, whatever is the by default time unit, 10 time units. After 10 time units, assign this. After 20 time units, assign. After 5 time units, assign this. Like this, it is happening. Now there will be a different result. Okay, now there will be a different result. So I simply run it. Now I see the result. Now result is different. Now how it is different, I can explain you step by step if you want. That's not a problem. This side, yeah. So I should be able to show both the windows parallelly. Now here, first statement when it is executed, display. Before this, actual statement is fifth statement. A should be assigned to A. But you can see that A, B, C, all three are X because time has not progressed. Time has not progressed. There is no timing parameter. But as soon as it goes to next statement, seventh statement, it is a delay of 10. But parallelly, is there any other statement also? There is a block. There is a block in this design actually. Just a minute, let me explain. I'll take the question. Here, timing parameter is 5. That means before this 10, 5 is happening. But here also, if I see now what happens when 15 is, I am displaying only D and E, so there is no E, so there is no question. After 5, then 10 comes. That is, this happens. Now here, after 10 units, B is assigned. But then after 10, B. So here actually A change has to happen after 10 time units. So when this statement is executed, now I should get A. So let us see after 10 what I'm getting. After 10 time units, if you see, A is A, but B and C are XX. A is changed because time has advanced. Time has advanced here. So A is changed. Assignment is been done only after time 10. 20, after time 20, only this B will be assigned to B. You can see here that after time 20 means 20 plus 10, 30. So at 30 instances, A becomes A, B becomes B. But still C and D have not been assigned. C and D are not. This is what is a blocking and non-blocking statements. So I explained you the main features of system Verilog, and I explained you how to execute the code. Now you can do the simulation of Verilog or system Verilog at your home, right? This is freely available. You need not pay anything to anybody. Now, any questions, sir? Somebody was asking the question. Sir, I heard some voice. I said, no, I'll ask. Like, anybody, any questions? Not exactly if you don't understand code, it is okay. You can write it afterwards. But now you got a power to execute the code and you got a tool set independent of this. If you are interested only in cadence again, then here you select a tool and simulator. You have got all kinds of companies available, including Aldec, Cadence toolset, Mentor Graphics, QSTA is also there, Synopsys, VCS is also there. So engine running in the back end is Cadence. That's the meaning. If you select that.
Hello, sir.
Yes. Yes, please go ahead.
What's the limitation of this then? Because this is the open to all. So
Yeah, limitation will be there. Limitation will be there. You will not be able to do each and everything. Means your code limitation will be there. First of all, they need, if you see logins, means Google login, etc. If you do, it might not allow you to execute code using some of the simulators. You have to have your professional ID of your institution. For example, my ID is my name @spit.ac.in. So your login has to be on spit.ac. That's it. Your login should be a professional login, nothing else.
yes,
So
I
you
have
log in
login first time.
Gmail login. Yeah, Gmail login. If you create Gmail login, then there is a problem. Then second issue, which I realized, there are some of the reports which you get using Questa, Scene, etc. Those things you will not get here. You will be able to see the result. That is okay, but it will not generate all kinds of reports and everything for you. It is for a basic learning purpose. So if you want to teach in your class, you can do that. But if you want to work in a professional environment or if you want to do a research onto this, then there is a problem. You will not be able to produce all results. Okay. That's what I have seen. Yes, ma'am.
And
Ma'am, loudly.
only for simulation and this functionality check we can go for this.
Exactly. Correct. You are right. Absolutely right. Absolutely right. Okay.
Sir, code coverage and all we can't do? Code coverage?
Code coverage is statements you can write, you can do that, but then you can't analyze the way a professional cadence toolset or the Questa sim will give. Questa sim will show you actual tabulated form, everything properly. Here you will not get in that manner. But code coverage in terms of text you can analyze. Here, you, if you write a code coverage, some examples and statements, you will get that. You can execute each and every functionality of system Verilog. That you can.
Okay, sir.
And the visualization will not be the way you want.
Okay, sir. Thank you.
Okay. Because I have executed codes for all these assertions, randomization, coverage, all everything. I basically teach course using ADA program, entire course using ADA playground. So you can learn like blocking, non-blocking, like this. What is happening on command prompt? Come to know the result. So you can teach it. But if somebody wants the reports, then difficult. Madam, anything else? Shaila, madam, Verilog programming now you will be able to do, I think, on this.
Madam is not there, I think, sir.
Achha, madam is not there. Okay. Yeah, she wanted yesterday. Yesterday we had a meeting at. I could not give him. Okay, then if nobody has any doubt or any other point of time, we can discuss this. No issues. I'm always available for you. I'm the one who is available for you 24/7. Okay.
Very nice lecture in new introduction to new software and this new system Verilog introduction. Very nicely introduced. Thank you.
Thank you. I took the benefit of opportunity. Now, sir will come back at 3:30. So,
That's good for the participants, sir. That is good for the participants. Na? Opportunity. Your opportunity is our benefit.
okay. I wanted to take 15 minutes, but almost 2 hours. Yes. Okay, it's okay.